So today's lecture is on introduction to NFA and DFA. So there are two types of finite automata. First is deterministic finite automata DFA and another is non-deterministic finite automata NFA. Right? So there are two types of finite automata. One is DFA and another is NFA. So we will see what is DFA. So, as you know, in your finite automata, you have a set of states and you have transitions also. And with the help of the transition, either the finite automata can accept or reject the input string. Similarly, in case of DFA, also, you have a set of states, you have different transitions. So, with the help of that transition, you can transit from one state to another state and depending upon the input symbol and then it will process the entire input string and finally either it will that string will be accepted or rejected by your DFA. Now here also the states are represented with the help of circles and transitions can be represented with the help of director arrows, right? But here uh, you should remember that there is a navigation from each state on each input symbol in case of DFA, right? So if you have two symbols in your input alphabet, then there will be a transition on both the input symbols in case of your DFA. DFA has many applications, like it can be used in speech recognition, it can be used in designing of compilers, it is also used in pattern matching and many more. So how actually your DFA looks, that we will see. So now consider the example that we want to design a DFA which will accept all the strings which will start with small a, which will start with a, and after a you can have any combination of a and b. Either you can have a combination of any combination of a and or b, or you may not have anything after a, but a is must, a is compulsory, and this is what is the meaning of this star. Star, it means here ax is written, so a, it means it should start with a, and x can be anything which you can x, it means it is any combination or any order or any number of times you can have a and or b, or you may not have it. So this is the meaning of this star, which is also called as a clean star. So if that is the case, and if you want to design a DFA for that, so you can say here you have the initial state Q0. So from Q0, you can move to, there is a transition on small a. You can see here you move to Q1, and Q1, you can say here you have a concentric circle. So it means the Q1 is a final state. So if you have only A, so still on this A, there is a navigation from Q0 to Q1. And as you are on Q1, it means the string is accepted. So single A is also accepted here. This is as per our requirement. And here you can see there is a loop, self loop to Q1, where it means that you can see here label as A comma B. So it means in Q1, whatever is the input, when you are on Q1 state, whatever is the input, A or B, you will remain here on the final state. So it is starting with A, as there is a transition from Q0 to Q1 on A. So if there is only one A, still you are on final state. And after A, whatever you have, any combination of A and B, still you are here on Q1. So this is satisfying our problem statement. And there is a transition on B. So you can see there is a transition from Q0 to Q2 on B. And because if it is following this transition, you will never reach to the final state. Why? Our condition is that it will accept only those strings which are starting with A. So if your string is not starting with A, it means if it is starting with B, so it will never reach to the final state. And that is the reason you can see here. Here we have Q2, and which is not marked as a final state. So this is the formal definition of DFA. As finite automata, here also we have five tuple Q's, your input alphabet, delta, Q0 and F. And meaning of all these five symbols is same as what is there in finite automata. So Q, it is nothing but the final state of all state. This is sigma, it is your input alphabet. And if you'll see the state transition function, it is same to your finite automata. Q0 is indicating your start state, and F, it is a set of uh, final state. And because this F will have a states which are coming from Q, so here it is mentioned that F is a subset of Q. So formal definition of DFA for the above discussed example. So here Q, you can say Q0, Q1, Q2. You can see here. Here we have three states, and that is the reason your capital Q contains these three states. Sigma, it is nothing but the input alphabet. So here we have only two uh, input symbols, A and B. So here you could see start state is Q0, and it is marked with this arrow. So if this arrow is to the Q0, it means Q0 is a start state. Then F1 is your final state, and F1 you could see it belongs to the Q, capital Q. Sorry, not F1, Q1. You can see it is a final state, and Q1 is from capital Q, and that is the reason here you can say here also it is mentioned F is a subset of Q. And Q1 you can see here, it is a final state, it is mentioned with the help of these concentric circles. And delta function or a state transition function is mentioned here. So if Q0 has input A, it is navigating to Q1. Q0 on input A, it is transiting to Q1. Then Q0 on input B, it is transiting to Q2. So on A, it is transiting to Q1. On B, it is transiting to Q2. Q1 on input A and B, you can see Q1 on input A and B, it is on Q1 only. So accordingly, you can see here. And Q2 on input A and B, again it is on Q2. So that is the reason you can see this transition function. So next type of finite automata is NFA, that is non-deterministic finite automata. So NFA also consists of the state, and you have a transitions that will tell which string is accepted or rejected. But here in case of NFA, you can observe that there are less restrictions than the DFA, and usually NFA is used to make the complicated finite automata to the simpler one. So the difference between NFA and DFA you can see here. See the diagram number 1. Here if this is your one state, and from this state you can see that there are two transition on the same input symbol A. So from this state you can navigate, you are transiting to some other state from A. This arrow it is showing that you are navigating to some other state, and whereas the self arrow tells that on input symbol A you are navigating to the state itself. So there are two transitions on the same input symbol, which you will not find in DFA. Then second difference you can find that NFA need not to have transition. The states of NFA need not to have transition on each input symbol, which is so in case of DFA. And in NFA you can find the transition on the empty string, that is epsilon. So this is epsilon here, it means there is no input to this particular state. So with no input also you can there is a transition in case of NFA, which is not so in your DFA. So these three are the basic differences between the NFA and DFA. In case of NFA you can have a multiple outcomes with the same language, right? But if still if a, any of the outcome, if it belongs to the, or if it is taking you to the final state, it means that string is accepted by the language and the diagram, that you will see that I can show you with the help of example. So it is the same example which we have considered earlier. So uh, this NFA will accept all the strings that will start with A, and after A you can have any combination of A and B. So this is your NFA for the same. Whereas in case of DFA, you would there was one more transition on B, because as it is said that in for each state of DFA there should be a transition on each input symbol, right? So here in case of NFA you can see there is no transition on B on this S. So this is how your NFA will look, and you could see that this diagram is simpler than the one which we were having for DFA. Then this is the formal definition of NFA, which is again similar to DFA. Again, it has got five tuples: Q, input symbol, state transition function, Q0, and capital F. The meaning of all these symbols is same as your finite automata or DFA. Then here you can see this is the formal definition of the same problem. This. So S and F, these are the two states you can see which is there in Q. Your input alphabet is consists of A and B. Start state is S. Final state is F, and transition functions you can see here. So on when S will have input A, it is transiting to F. There is no transition on B from S. There is no transition on epsilon from S. Um, from state F, you can navigate on input symbol A and B, and you are navigating to the same state. And on epsilon, there is no transition. Now, equivalence of NFA and DFA. You can say the NFA and DFA are equivalent if they are accepting the same language. And same language, as you know, what is the meaning of language? It is nothing but the collection of words or the strings, right? So if NFA whatever set of strings the NFA is accepting, if same set of strings if your DFA is also accepting, then we'll say that NFA and DFA both are equivalent, right? And collection of those accepted strings, we call it as a language. And every NFA you will find there is a equivalent DFA. So these two diagrams are there in front of you. So if you'll see this NFA, it is accepting the string as 0 0, and it is accepting 0 1. From here there is a transition to Q3, but Q3, because it is not a final state, so it will not accept the string like 0 and then the number of ones, multiple ones. So such type of string will be rejected by the NF, and that is the reason you will not find those strings here in L1. So L1 consists of only two strings, 0 0 and 0 1. If you will consider this DFA, So in this case also, it is accepting the two strings 00 and 01. So both the NFA and DFA, they are, because they are accepting the same language, we'll say that the NFA and DFA both are equivalent.